How we doing, guys? Just looking at exercise 13E, Fundamental Applied Maths, page 3232. We're going to look at questions 3 and questions 5. So to start off with, question 3 asks us, a particle of mass m is suspended from a point P on a light on the ceiling by means of a light elastic string. This is one of these magical strings with no mass that do not stretch that we're using all the time in these things. Oh, sorry, elastic, it does stretch, excuse me. Of natural length d and elastic constant 49m over d. It's pulled down a distance 8d over 5 below p and released from rest. Show that it will perform simple harmonic motion as long as the string remains taut, and then find in terms of d when the string becomes slack for the first time. Okay, so the only difference between these questions and the ones we've seen up to now are that we've got gravity now acting downward. So this is just simple harmonic motion in this direction, in a vertical direction rather than a horizontal direction. So to find our equilibrium point, first of all, we're going to say the downward force, gravity, has to equal the upwards force, which is Hooke's law. That's 49m over d. That's our spring constant times the length of our spring is whatever our equilibrium length is. I've called it A here, minus the natural length d. And what we find here is, first of all, mass cancels. And if we multiply, 49 is 5 times 9.8. So I'm going to cancel that and put a 5 in there as well. So that's just a 1. And when I cross multiply now, I'm going to get d equals 5a minus 5d. So 6d is 5a. And our equilibrium position A is at 6d over 5. Okay, now we're told in the question that it's pulled down a distance 8d over 5 below p. Okay, so we're pulled down to this length here. So if A is 6d over 5, well then we're pulled down an extra 2d over 5 is that's going to be the amplitude of our motion. Okay, so that's our equilibrium point. It's going to move around that point, maximum displacement and maximum acceleration down here, maximum velocity at this point. Afterwards, it's slowing down under gravity on the way up. It will reach a point here where it goes up, and if it reaches a length less than d, the string is going to become slack, and we'll no longer be looking at simple harmonic motion. We'll be looking at a problem where we've just projected something into the air. So a UVAS problem. So to show that this undergoes simple harmonic motion, we're going to say the force is down minus the force is up. What are they? Well, the downward force is mg, which we've already seen, minus the upward force is, so there's our length, 8d over 5 is the length of the string now. So it's our spring constant, 49m over d, times the length of the string, 8d over 5, times some length of the string. So sorry, we're going to say it's our equilibrium length, plus some distance x beyond that equilibrium length, which is what we always do to show simple harmonic motion. When it's some distance beyond equilibrium, what happens? So we're going to say it's 6d over 5 plus x. That's some distance over beyond equilibrium is the length of the string, minus the natural length, which is d. Okay, so my apologies there. So what are we getting here? We are getting mg minus, now I'm going to write that as 5mg, okay, so 5g for 49 over d, times 6d over 5, minus 5mg over d times x, and then minus by minus gives plus 5mg over d times d. Okay, so that cancels straight away. So what do we get there? Well, we get mg minus, okay, d's cancel and 5's cancel, so we get 6mg minus 5mg x over d plus 5mg. 5mg and mg is 6mg, take away mg. These all disappear. Okay, so we're left with the net force, which is mass times acceleration, and this particle just has mass m, equals minus 5mg x over d. Okay, and masses cancel there. We get the acceleration is minus 5g over d x. So it's some constant multiplied by the displacement. Acceleration is proportional to displacement in the opposite direction. So that's simple harmonic motion that we've demonstrated there. Omega squared is 5g over d, which is 49 over d. I'm going to go back to that because when we take the square root, omega is going to be 7 over the square root of d. Okay, so show that it does simple harmonic motion. Done. We've got omega. We know that the amplitude of the motion here is this 2d over 5. Okay, we're going to need this in the next part of the question. So the amplitude is what we've stretched beyond equilibrium. That's 2d over 5. So the next part of the question asks us, find in terms of d when the string becomes slack for the first time. Okay, well that's when we've gone up beyond our equilibrium point to a position where we are a distance d below p. Okay, when the distance below p is less than or equal to our natural length, that's when it goes slack. Okay, well to get there, how far are we from our equilibrium point? Well, if our equilibrium point is 6d over 5, d you can think of as 5d over 5, so we are 1d over 5 beyond our equilibrium point. Against the direction we call positive, we call down positive at the start of the problem. So that's a negative distance from our equilibrium point. Okay, there's our 0 point. Downwards positive, upwards negative. So when the string becomes slack for the first time, we're going to choose between our usual a cos omega t and x is a sine omega t, and as we seem to be doing for all of these, we'll ignore that one. This one is where we're starting at an extreme point, okay, which is what we're doing. So we want to say x is minus d over 5. Okay, so that's our displacement. Needs to be negative d over 5. Our amplitude is 2d over 5. Cos of omega is 7 over root d. Times t. Okay, so that's what we want to solve to find the time at which the string becomes slack when the displacement is minus d over 5 for the first time, so the first value that we get for that. So if we cancel our 5s, first of all, multiply both sides by 5, divide both sides by d, we're going to get minus a half is cos 7 over root d t. Okay, and let's see if our calculator gives us the positive answer for that one. Inverse cos, so we want to say 7t over root d equals minus 0.5. Cos inverse minus 0.5. So our inverse cos of minus 0.5 is 2 pi over 3. Okay, so it's 120 degrees in degrees, so that's 60 is our reference angle if you do cos inverse of a half. So that's 120 or 2 pi over 3. Okay, so 7t over root d equals 2 pi over 3. So the first time the string becomes slack, multiplying through by root d and dividing by 7 is 2 pi over 3 multiplied by root d divided by 7. That's 2 pi root d over 21. Okay, there's the first time the string becomes slack. Question 5 involves some new stuff that we're going to have to talk about if we haven't looked through the hydrostatics chapter yet. So a cubic block of wood of side H and relative density S floats in water with all sides either vertical or horizontal. So the relative density is what fraction of the density of water is it? So a relative density of 1 means the same density of water. The density of water is 1,000 kilograms per meter cubed. So down here we've got a relative density of 0.6 in this question. So we're going to go with 600 kilograms per meter cubed is the density. Be careful in this question, by the way, because they've got mixed units. They're working in centimeters. Convert all them to meters. Okay. So our density is 1000 S is the density of our block. Okay, so density of water is 1000 kilograms. Multiply that by our relative density, we get 1000 S. Floats in water with all sides either vertical or horizontal. It is depressed a distance x into the water and released from rest. Show that it will perform simple harmonic motion. Okay, so we need to talk about what keeps this thing floating. Okay, so obviously its weight is acting downwards. We get mg acting downwards. The upward force is a force called a buoyant force or an upthrust. Those of you studying physics, the physics curriculum will know Archimedes' principle. When a body is submerged in a fluid, experiences an upthrust equal to the weight of the displaced fluid. Okay, so fluid here can be a gas or a liquid. So what we're going to be interested in, that buoyant force, is the weight of whatever water this little section here of the block has moved out of the way, displaced. Okay, so if you remember putting things into displacement cans in first year to measure their volume, the amount of water that would overflow from the can if you put this block into it. So a few things about this. Density of water, 1000 kilograms per meter cubed. The volume of our block, because it's three sides of side H, it's a cube, so it's going to be H cubed. The mass of our block is density multiplied by volume. Okay, so 1000 S is our density, kilograms per meter cubed, multiplied by H meters cubed gives us 1000 S H cubed. That's the mass of our block. So when we say the weight of our block is mass times gravity, that's going to be 1000 SH cubed G. The volume of displaced water, well, if we look at that here, when we're at distance d, so d is our equilibrium distance below the water, the volume of displaced water is going to be length by width by height for a cuboid of length h, width h, and height d. So the volume of displaced water is going to be h squared d, and the mass of displaced water is going to be h squared d times the density of the water, which is 1000 kilograms per meter cubed. That should be in meters cubed, is our unit there. So that's going to be 1000 h squared d. And then finally, what we're interested in is the weight of the displaced water. This is the downward force. The weight of the displaced water will be equal to the upward force, the upthrust. So the weight of our displaced water for us is mass 1000 h squared d times g, okay, mg, mass times gravity. So that's the weight of the water that this bit is pushed out of the way, as it were. Okay, so that's all the hydrostatics out of the way. We can get back to some simple harmonic motion now. What we want to show is that if it's depressed a distance x beyond its equilibrium point, so d plus x, okay, so it's depressed that distance, what are the forces acting? We need to find that equilibrium point first. Okay, so to find our equilibrium point, we're going to say forces up have to equal the forces down. So our upward force is the buoyant force, which is typically going to be given by the the density of the water times the volume of the displaced water times G. So you see that V rho G quite a lot for that one. Okay, so that's going to be the volume. The volume of the water is H squared D times the density is 1000 kilograms per meter cubed times G. and that has to equal the downward force, which is the weight of the block, which is 1000 sh cubed g. Now, if you're thinking I've started this one with all the letters, that's true. There's only 2 questions of this type in the book. This one has all the letters. The next question has some more numbers. It's a little bit more concrete, so I'm going to let you work on that one yourselves. So let's find our equilibrium position D. Well, we've got a common 1000, we've got a common G, and a h squared that's common to both sides. So we get ourselves D equals S multiplied by H. Okay, so that's our equilibrium distance. Okay, we'll move on over here. So what about to show that it performs SHM? We're going to say, well, what's the net force? And taking downwards as our positive direction, we're going to say the force is down minus the force is up will give us our net force. The downward force is the weight of the thing, which is consistent throughout. It is 1000 sh cubed minus the upward force is whatever that buoyant force is. Okay, so that's B here. But remember, we've now submerged it an extra distance x. Okay, so that buoyant force, well, the volume of displaced water has now become, so it's volume times density times g, but our volume has now become h squared. Instead of h squared times d, it's h squared times d plus x. Okay, times the density of water, 1000, times g is, times g. Okay, so if we keep working through here, what are we going to get? We know that our equilibrium distance, d, is going to be sh, so we can sub that in. We're getting 1000 sh cubed minus h squared times d, which is sh now. So that's going to be sh cubed times 1000g minus h squared x times 1000g. Okay, so our net force here, if you'll notice that 1000 sh cubed, now something's gone funny here, force down, the buoyant force is the weight of the displaced water. I left out a g. Okay, so it's the density times the volume times g, so sorry about that. Okay, so what we're getting here is 1000 sgh cubed minus another 1000 sg, and that's h squared by h is h cubed, minus 1000 gh squared x. Okay, and of course these cancel, and we're left with the net force, which is just the mass times the acceleration, is going to be minus 1000 gh squared x. Now remember, the mass of the block is 1000 s times h cubed. Okay, so sorry, that's here. The mass of the block was 1000 sh cubed. So that becomes 1000 sh cubed equals minus 1000 gh squared x. So dividing through mass times acceleration, we just want acceleration, so the thousands will cancel, and we're going to see h squared cancel with h squared here. So let's just write that again. SHA equals minus g x. Okay, and our acceleration is going to be minus g over sh x, which is simple harmonic motion. Okay, because we've got our acceleration is proportional to our displacement and in the opposite direction. We also get out of that omega squared is g over sh, and omega is the square root of g over sh. I think the question then asks us for the periodic time. And find an expression for the periodic time. So T is 2 pi over omega, which is 2 pi divided by that whole mess there, which I'm going to say is root G over root SH. Multiplying top and bottom by SH, you get 2 pi root SH over root G. Or, well, 2 pi root SH over G. Okay, so there's our expression for the periodic time. The second part of the question says, if the water had been a liquid of relative density K, what would the periodic time have been? Okay, so now we're saying rather than displacing water, we're displacing something else. Let's say oil, for example, with a relative density of K. Okay, so the upthrust changes now because the weight of the displaced fluid changes when the fluid has a different density. So the upthrust now, B, will equal the volume of the displaced fluid. That hasn't changed. That's going to be, for our equilibrium volume, it's going to be h squared d, whatever our equilibrium distance is, times the density now is 1000 K. Okay, 1000 times the relative density of the water, or the fluid, times G. Okay, so there's our buoyant force. The weight, the mass of the block hasn't changed. Okay, so that's still 1000 SH cubed. And if we say we need our equilibrium position to be that the force up equals force down, you're saying the force up is the buoyant force, which is 1000 K G H squared D, and our downward force is 1000 SH cubed. Okay, so our thousands cancel. H squared cancels out of that and cancels out of that. And we get ourselves that, what were we looking for there? I've lost my D, have I? Oh, sorry, D there, yeah. So we get KGD equals SH. And our equilibrium distance is now SH over KG. Okay, so there's our equilibrium distance, which means when we now engage simple harmonic motion, when we push it down a little bit beyond that, we're going to say that the forces, the net force is downward force minus our upward force. Our downward force is still going to be the weight of the block, which is 1000 SH cubed. Sorry, that's the mass of the block, so it's going to be 1000 SH cubed times G. 1000 SH cubed is the mass times G, minus the upward force is the buoyant force now, which is given by the volume of displaced fluid, which is d plus x this time, times h squared. Okay, so there's the volume of displaced fluid times the density of our displaced fluid is now 1000 K times G. Okay, so we are going to get ourselves 1000 SH cubed G minus, let's make that SH over KG for D, there's our equilibrium distance, plus some extra distance times H squared times 1000 kg. Okay, so we're going to say that is 1000 SH cubed G minus 1000 SH cubed over kg multiplied by, so 1000 kg I still need to include, and you see those kg's cancel, minus 1000 k g 1000 kg. Now I knew I'd gone wrong somewhere. Sorry about this. Now our downward force is, that is the mass of the block. I should have said the weight of the block was our downward force, so I knew there was something wrong there. G's have cancelled there, so D is only SH over K. So sorry about that. So we've no G in the bottom here to cancel, so that G stays where it is. Minus 1000 kg h squared by x. Okay, and the reason I kind of could see something was going wrong was because you normally expect these terms to cancel, and they do. 1000 sh cubed g, 1000 sh cubed g, when you take them away, is 0. So our net force, which is our mass times acceleration, is minus 1000 kg h squared x. Okay, well, our mass, remember, for our block is 1000, we have it over here. Mass of the block is 1000 sh cubed. So that's 1000 sh cubed times the acceleration is minus 1000 kgh squared x. So what cancels? H squared with h squared here, 1000 with 1000, and we get ourselves that the acceleration is minus kg x divided by sh. Okay, so all of these things are constants. K is just how much denser our fluid is than water. S is how much denser our block is than water. H is the height of the block, and G is gravity. So these are all constants, which means acceleration is a negative multiple of the distance. Okay, that is proportional to the distance and in the opposite direction, which is SHM. Okay, our omega squared is kg over sh, which means omega is kg over sh is the square root of all of that, and t, which is 2 pi over omega, is going to be 2 pi. I'm just going to assume we can invert this fraction because we're dividing. So multiplied by sh divided by kg, okay, the square root of. And there's our expression for the period if the density changes. Okay, so if the density of the water changes, the period of our motion also changes from, well, I've lost the first part of the question, so we won't worry about our period of the motion. Okay, but that's our new period anyway. I think our old one was 2 pi sh over g, so just that k lands in down the bottom. Okay, plenty of other questions in the section. I'd encourage you to give them a go, particularly the hydrostatics one there. See you next time. Bye bye.